Hello everyone, I am Prasanna Kumar from CSM Section C. Today I will present my tech talk on the topic higher order non-homogeneous equations, which is part of ordinary differential equations and vector calculus. Differential equations are important mathematical tools used to describe how quantities change over time. They are widely used in engineering, physics, control systems, and modern AI models. In this presentation, I will explain higher order differential equations, methods of solving non-homogeneous equations and their applications in engineering systems. Introduction to higher order differential equations. Higher order differential equations are equations that contain derivatives of second order or higher. These equations are very important in modeling dynamic systems such as mechanical vibrations, electrical circuits, and aerospace systems. A general nth order linear differential equation can be written as an of x into y power n plus so on plus a1 of x y dash plus a naught of x y is equals to g of x. Here the function g of x represents an external forcing function which makes the equation non-homogeneous. The system of such equations consists of two parts, the complementary solution and the particular solution. Together they form the complete general solution. Classification of linear differential equations. Linear differential equations can be classified into homogeneous and non-homogeneous equations. If the function g of x equals 0, the equation is called homogeneous. If g of x is not equal to 0, it is called non-homogeneous equation. Homogeneous equations follow the principle of superposition, meaning solutions can be added together to form a new solution. Non-homogeneous equations require special methods such as undetermined if coefficients are variant of parentheses. When the coefficients of the equation are constant, the equations become easier to solve using characteristic equations. Complementary solution. The complementary solution is obtained by solving the associated homogeneous equation. For equations with constant coefficients, we assume a solution of the form y is equals to e power rt. Substituting this into the differential equation gives a characteristic equation. The roots of this equation determine the type of solution. If the roots are real and distinct, the solution contains exponential terms. If the roots are repeated polynomial terms are multiplied with exponential. If the roots are complex, contains the solution contains sine and cosine functions representing oscillatory behavior. Method of undetermined coefficients. The method of undetermined coefficients is used to find the particular solution of non-homogeneous differential equations. This method works when the forcing function g of t is a polynomial exponential sine, cosine, or a combination of these. In this approach, we assume a trial solution with unknown constants. These constants are called undetermined coefficients. By substituting the trial solution into the differential equation, we can determine the values of these coefficients. This method is simply and effective for many engineering problems. Polynomial forcing function. When the forcing function is a polynomial, we assume the particular solution is also a polynomial of the same degree. For example, if the forcing function is a quadratic polynomial, we assume a quadratic trial solution. If the complementary solution already contains a similar term, we multiply the trial solution by t to avoid multiplication. After substituting the assumed solution into the differential equation, we compare different coefficients of like parts of t. This allows us to determine the unknown constants. This method is often used in control systems and signal modeling. Exponential and trigonometric forcing. If the forcing function is exponential such as e power at, we assume a trial solution of the same form. If the forcing function involves sine or cosine, we assume a combination of sine and cosine terms. However, if the assumed trial solution is already part of the complementary solution, we multiply it by t. This situation is called resonance. These types of forcing functions appear in systems involving vibration, electrical circuits, and oscillating signals. Variation of parameters. The variation of parameters method is a more general technique for solving non-homogeneous equations. Unlike undetermined coefficients, it works for any type of forcing function. In this method, the constants in the complement arbitrary solution are replaced with functions of time. These functions are determined by solving a system of equations. The process involves calculating the Rorskian determinant of the solution set. Although the method mathematically complex, it is very powerful and widely used. Variation, variation of parameters example. For a second order differential equation, we assume the particular solution in terms of two functions. These functions are determined using equations derived from the complementary solution. The Rorskian determination helps verify that the solutions are linearly independent. Once the functions are found, they are submitted back into the assumed form. This produces the particular solution of the non-homogeneous equation. This method is useful when the forcing function cannot be handled by simpler techniques. General solution of non-homogeneous equations. The complete solution of a non-homogeneous differential equation is the sum of two parts. The first part is complementary solution, which represents the natural behavior of system. The second part is the particular solution, which represents the response of external forces. So the general solution can be written as y of t is equal to y dash y underscore c of t plus y underscore p of t. Initial conditions or boundary conditions are then applied to determine the unknown constant. Applications in control systems and AI. Higher order differential equations are widely used in engineering and control systems. They describe the behavior of systems such as robotic arms, aircraft dynamics, and electrical circuits. In artificial intelligence, differential equations are used in neutral ordinary differential equations where system states change continuously. These equations help predict system behavior under different input. Understanding them helps engineers design stable and efficient control systems. Laplace transform method. The Laplace transform is another powerful method used to solve differential equations. It converts differential equations in the time domain into algebraic equations in the S domain. This transformation simplifies calculations and makes it easier to include initial conditions. After solving the equation in the S domain, we apply the inverse Laplace transform to obtain the time domain solution. This technique is widely used in signal processing, circuit analysis and control engineering. Laplace transform for non-homogeneous equations. When solving non-homogeneous equations, the Laplace transform is applied to both sides of the equation using properties of Laplace transformation. Derivatives are converted into algebraic expressions. We then solve the resulting equation for the transform function. Partial fraction decomposition is often used to simplify the expression. Finally, the inverse Laplace transform is applied to obtain the final solution. This method is especially useful for problems involving step functions or impulse inputs. Resonance and force oscillations. Resonance occurs when the forcing frequency equals the natural frequency of the system. In such cases, the amplitude of oscillations may increase dramatically. This can cause serious problems in engineering systems such as structural failure in bridges or mechanical systems. To prevent this, engineers include damping mechanisms that reduce oscillations. Understanding resonance is important in mechanical design, electrics, and aerospace engineering. Numerical methods. Some differential equations are too complex to solve analytically. In such cases, numerical methods are used. Examples include the Runge-Kutta method and finite difference methods. These methods approximate the solution at discrete time intervals. Modern software such as MATLAB, Python, and Simulink is commonly used for numerical solutions. These tools help engineers visualize system behavior and analyze complex models. Case study: Aircraft pitch dynamics. A practical example of differential equations is aircraft pitch dynamics. The pitch motion of an aircraft can be modeled using a second order differential equation. This equation includes terms representing inertia, damping, and restoring forces. External for control inputs from the pilot or autopilot act as forcing functions. By analyzing this equation, engineers can design stable flight control systems. Summary and key takeaways. To summarize, higher order non-homogeneous differential equations are important mathematical tools for modeling real-world systems. They are solved using methods such as undetermined coefficients, variation of parameters, and Laplace transformations. These equations help analyze system behavior, stability, and response to external forces. They have many applications in engineering, robotics, aerospace, and artificial intelligence. Understanding these concepts helps engineers design advanced and reliable systems. Thank you for listening to my presentation. I hope this presentation helped you understand the concept of higher order non-homogeneous differential equations and their applications. Thank you.